whether counting galaxies in the universe or tracking requests to a web server. Scientists rely on the Poisson distribution to model random events. But where did it come from? Welcome back to Drawing Distributions. In this video, we'll explore the origins of the Poisson distribution by unraveling the analysis of the mathematician it was named after. Along the way, we'll develop the key intuition as to why it is an important distribution for modeling rare events. Poisson was a 19th century French mathematician, a student of Laplace and Lagrange, whose talent for mathematics was noticed from a young age. Poisson's contribution to science is recognized by an engraving on the Eiffel Tower that bears their name. In 1837, they published a detailed body of work titled Researches into the Probabilities of Judgments in Criminal and Civil Cases. This book explained how probability theory could be used to describe decisions made in court. The derivation of the Poisson distribution starts in section 73, where they consider the following calculation. I return to the case of constant chances P and Q of the events E and F, and consider the probability P that in mu trials E arrives not less than m times, and F not more than n times. Let's break this down into two parts. The first, considering a single Bernoulli trial, and the second, extending this to multiple trials. A Bernoulli trial is an experiment with two outcomes. Think about flipping a coin with heads on one side and tails on the other. Together, these outcomes form the sample space. Assuming that the coin is fair, then heads is just as likely as tails, equal to a probability of 1/2. Returning back to Poisson's question, then the events E and F form the sample space. The probabilities assigned to these outcomes must be complementary, so if the probability of E is P, then the probability of F must be 1 minus P to ensure they sum to 1. To describe this mathematically with a Bernoulli distribution, we need to introduce a random variable, call it x, that maps the outcome E to 1 and F to 0. We can say that x is a Bernoulli distributed random variable with parameter p, where p is the probability that x takes on the value 1. Let's say that p equals 0.75. Then we can visualize the probability mass function like this. We now know how to describe the first part mathematically as a single Bernoulli trial, but the second part requires us to take this a step further. This is because the probability P is associated with the event E occurring at least m times in some fixed number of trials. So, instead of a single Bernoulli trial, we need to think about performing multiple trials. Let's return to the coin flip example and look at the probability of 2 heads in a total of 4 flips. Each flip can be modelled with a Bernoulli distributed random variable, with a probability of heads equal to 1/2. This means that x sub I takes on the value 1 for heads and 0 for tails. Then, the number of heads in 4 flips is simply the sum of these random variables. If we call this sum S, then the probability we are looking for is the probability that S equals 2. We can answer this by enumerating the different ways that 2 heads can occur in 4 trials. The probability of 2 heads in 4 trials is the same as the probability of 2 heads and 2 tails. This is equal to the probability of heads squared times the probability of tails squared. In this example, we assume a fair coin, so this works out to 1/2 raised to the 4th power. We are allowed to multiply the probabilities because the Bernoulli trials are independent of each other. We have shown exactly 6 possible ways of getting 2 heads in 4 trials, so the probability we are after is 6 times this number, a value of 3/8 or 0.375. A specific ordering of heads will typically have a low probability of occurring, but if order does not matter and we are only interested in the number of heads, we need to multiply this probability by the number of different ways it can happen. These are exactly the probabilities modeled by the binomial distribution. Probability theory tells us that sums of Bernoulli distributed random variables follow a binomial distribution. The probability mass function of the binomial distribution is the product of m success probabilities p and mu minus m failure probabilities, multiplied by the number of ways to get m successes in mu trials. This coefficient is known as the binomial coefficient, or n choose k. It counts the number of ways that k items can be chosen from a total of n, if order does not matter and each of the n items are different. Now, remember that Poisson was interested in the probability of getting at least m successes in mu trials, not just a specific number of them. So how do we use the binomial distribution to answer this? To illustrate, let's consider a binomial distribution describing the number of successes in 10 trials, each with a success probability of 0.75. If we then wanted to calculate the probability of at least 7 successes in 10 trials, for example, we simply sum up the relevant values, from 7 to 10. More generally, this means that Poisson's probability p is equal to the sum of the values in the upper tail of the binomial distribution, starting from m successes. But Poisson was not happy with this representation of the probability p because it is difficult to transform this expansion into an integral to which, if m and n are very large numbers, the method of section 67 can be applied. Unfortunately, Poisson does not provide much explanation here, but we can assume that they wanted to express p in terms of definite integrals that can be approximated using Laplace's method, which they introduced in section 67. As we'll see later, the reformulation of the probability p is not needed to derive the Poisson distribution. But by following Poisson's analysis, we gain a different perspective on the problem, while also learning more about the binomial distribution. Say that p equals the probability of at least 2 successes in 4 trials. We now know this can be calculated by summing the probabilities of a binomial distribution from 2 to 4 successes. Let's write down all the different ways that at least 2 successes can occur in 4 trials, and sort them by how many successes they contain, where green represents success and orange represents failure. We started with the probability of at least m successes in mu trials. This can be expressed equivalently as the mth success occurring on or before the muth trial. Let's go back to our example and sort the events by what trial the second success occurs on. On the left, we have all events where the second success occurs on the second trial, the third trial in the middle, and the fourth trial on the right. The key observation is that we have not needed to add or remove anything. And because the underlying sample space is still the same, the probability of the second success occurring on or before the fourth trial must be equal to the probability of at least 2 successes in 4 trials. If there are at least m successes, then the minimum of just m successes happens when the mth success occurs on the final trial. Clearly, it can also happen before this trial, which allows for at least m successes. The problem with the statement is that it is not clear what we are counting. The number of successes is always equal to m. But We can reframe it in terms of failures by using the relationship between successes and failure counts in a fixed number of Bernoulli trials. That is, at most n failures before the mth success. Let's return to our example one more time to see why this makes sense. If the second success occurs on the second trial, this is the same as 0 failures before the second success. If the second success happens on the third trial, then 1 failure must have already occurred before it. Similarly, if the second success lands on the fourth trial, then 2 failures must have already occurred. It is in this way that Poisson reformulated the probability P from at least m successes in mu trials to at most n failures before the mth success. If we let t be the number of failures before the mth success in a sequence of independent Bernoulli trials with success probability p, then t follows a negative binomial distribution. The parameters are m, the number of successes, and p, the probability of success in each trial. Unlike the binomial distribution, which counts the number of successes within a fixed number of trials, the negative binomial counts the number of failures that occur until a fixed number of successes is reached. This means the total number of trials is random and depends on when the mth success happens. We can use what we've learnt so far to write down the probability mass function of the negative binomial distribution. The probability of m successes is equal to p raised to the mth power, and the probability of k failures is 1 minus p raised to the kth power. We also need to multiply by the number of different ways these k failures can happen. There are m successes and k failures, but the mth success is always fixed to the final trial. This means we want the number of ways that k failures can occur in m plus k minus 1 trials. Now here comes the cool result. We have followed how Poisson reformulated the probability p from at least m successes in mu trials in terms of the upper tail probabilities of a binomial distribution to at most n failures before the mth success in terms of the lower tail probabilities of the negative binomial distribution. Let's visualize this to make sure that we really understand this relationship. On the left is the probability mass function of a binomial distribution with success probability p equal to 0.75 and total number of trials mu equal to 10. And on the right is the probability mass function of a negative binomial distribution with the same success probability and stopping success parameter m equal to 0. M is then incremented from 0 up to 10. For each value of m, we calculate the sum of the probabilities of the binomial distribution from this value. This is equal to the probability of at least m successes in 10 trials. At the same time, we update the stopping success parameter of the negative binomial distribution with m to reflect the minimum number of successes and sum its probabilities from 0 to n, where n is equal to the total number of trials minus the current value of m. This is the probability of at most n failures before the mth success. For both distributions, the probabilities included in these calculations are coloured in green, and the ones excluded in orange. In each case, the sums are equal. This shows the key relationship between the upper and lower tail probabilities of the binomial and negative binomial distribution. In section 81, Poisson questions how the probability p behaves when the chance of failure is small, but the total number of trials is large. Suppose that the probability of f is very low. If the number mu of the trials is very large, the ratio n over mu of the number of the arrivals of f to mu will also be very small. Mathematically, this is translated into a limit calculation. A limit is a way of analyzing the behavior of a function as one or more of its input variables increase or decrease towards a target value. To answer this question, we need to take the limit of the cumulative distribution function of the negative binomial distribution as the number of trials mu goes to infinity. We can use some rules about limits to make this easier. For example, the limit of a product is the same as multiplying the limits, and the limit of a sum is the same as adding the limits. This allows us to break the problem into smaller calculations which we can solve one at a time before combining the results. Before doing this, we need to make some careful substitutions. Poisson introduces a new variable, w, equal to the expected number of times the event f occurs in mu trials, and they choose to keep it constant for any value of mu. The effect of this is that when mu increases, then the probability of f, equal to q, must decrease in a controlled way to keep w constant. This means that as the number of trials increases, the probability of the event f decreases. F is a rare event with a constant average rate w. Let's start with the first limit. We can substitute m equals mu minus n and split the calculation into two limits using the product rule for exponents. At the same time, we write p as 1 minus q. Next, using the relationship between w, q, and mu from earlier, we know that q can be written as w divided by mu. The limit of the second term is equal to 1. As mu gets large, the fractional term approaches 0. The first term is a well-known characterization of the exponential function, equal to e raised to negative w. The second calculation is a sum of limits. To keep things simple, let's calculate the limit of the term at the jth index, and then substitute this result back into the sum. To begin, we can replace q with w divided by mu, and expand the binomial coefficient. Since the values of j and w do not depend on mu, they can be brought outside the limit. Additionally, the factorial in the numerator of the fraction is partially cancelled out by a matching term in the denominator. The remaining multiplications can be written as a product. As mu grows, the contribution from the constants within each term of the product becomes negligible because they do not scale with mu. This means that each ratio approaches a value of 1. The result is w raised to the jth power divided by j factorial. Multiplying these two calculations together completes the derivation. Let's visualize it. We can set the expected number of events w equal to 2.5, for example, and plot each probability in the sum. These values are actually the probabilities of event counts described by a Poisson distribution. Here is the probability of 0 events, 1 event, 2 events, and so on. The Poisson distribution is a discrete probability distribution with a single positive parameter w equal to both its mean and its variance. The distribution assigns probabilities to counts of events, which are the set of natural numbers, including 0. Using all the pieces we've assembled, we can describe it precisely. It counts the number of events in a long sequence of Bernoulli trials, where the probability of an event in any single trial is tiny, and the expected number of these rare events stays constant no matter how many trials we consider. Let's end with two concrete examples. Suppose that you are modelling the number of times one might roll a 6 in 10 trials, where each trial consists of rolling a fair 6-sided dice. A natural starting point is the binomial distribution, with success probability p equal to 1 over 6 and total number of trials mu equal to 10. The limit tells us that as the event gets rarer, such as rolling all 6s from 3, 4, or even 10 dice in a single trial, and the number of trials increases so that mu times p remains constant, then a Poisson distribution with mean mu times p is a good approximation to the binomial distribution. See how the white circles begin to match the shape of the Poisson distribution in green? This is the limit at work. If we frame rolling a 6 as a failure and anything else as a success, then we can model how many times we might get a 6 before the 10th time anything but a 6 is rolled using the negative binomial distribution, with stopping success parameter m equal to 10 and success probability equal to 5/6. In this case, the limit tells us that if both the success probability and stopping success number are large, then the Poisson distribution, with mean equal to the expected value of the negative binomial distribution, is a good approximation. Once again, notice how the probabilities converge to the green Poisson outline. For finite parameter values, the binomial and negative binomial are distinct distributions. But in the rare event limit, the difference vanishes. Counting rare events over infinitely many trials is indistinguishable from counting until infinitely many successes. All that is important is that the rare events occur independently with a constant average rate. This is the key idea behind the Poisson distribution. That's all for this video. You can find the information I used to create and research this video in the description. Please like and subscribe if you found this video useful, and consider sharing with others who might benefit from this content. Thanks for watching.